Hi guys, welcome to your last math lesson of 5th grade. I know that you guys will want to have a box of tissues handy for this one because I know how much you all just love math and hold it dear to your hearts, and I know that this is just heartbreaking news for you all. So I'm sorry to be the ones to tell you, but yeah, you made it. This is it. So let's get to it, shall we? We're going to be covering 2 lessons today, so haha, gotcha. But we're actually going to be starting with the second one first. So go ahead and open up to page 308 in your books. And we're going to be talking about properties of two-dimensional shapes in this lesson. And then we're also going to be distributing shapes by properties, I guess. So, so on page 308, at the top it says, how do we group polygons into categories? So first let's talk about polygons. Polygon means a shape. Poly actually is Latin meaning many, and gon actually in Latin means sides. So polygon literally translates to many sides. And so a polygon is a shape. It can have any number of sides, but there are a few rules that polygons have to follow. The first rule is that all of the sides have to be straight. So a shape like this would not count because it has curved sides. So polygons have to have straight sides. That's the first rule. The second rule is that they have to be closed. So if you had a shape like this, although I have straight sides, it is not closed. There's an open space, so it would not be considered a polygon. Now, if I were to add some straight lines to it, I could make it into a polygon, but polygons, the second rule is that they have to be closed. So those are a couple of rules about polygons. And we're going to be talking about some specific names of polygons and what makes those polygons special and unique, that they deserve their own name. So polygons are grouped into categories by their attributes or properties, such as the number of sides or angles. The side lengths and the angle measurements are also components in there. All polygons in the same category share certain properties. Some properties of polygons are described in the table below. So let's break that down a little bit. All polygons in the same category share certain properties. So for example, all triangles have 3 sides and 3 angles. All quadrilaterals have 4 sides and 4 angles. But within both of those categories, there are subcategories of more specific attributes. So for example, under the subset of quadrilaterals, you could have squares, which have 4 equal sides and there we go, 4 equal sides and all right angles. You could have rectangles with 2 pairs of equal sides and all right angles. You could have parallelograms that also have 2 sets of equal sides but no right angles. You could have trapezoids, which have 2 parallel lines and 2, yeah, I think that's the attribute. I think they're, anyway, you get the idea. So in the table on page 308, it says property, description, and then there's a picture as an example. So the property of a scalene triangle is that it has no sides of equal length, and so you have something that looks kind of like this. None of the 3 sides are equal. That is called a scalene triangle. The next one down says isosceles, at least 2 sides of equal length. So that means that an isosceles triangle could look something like this, in that it has two sides that would be the same length and a third side that may or may not be the same length. Notice that it says at least two sides. So triangles only have three sides, so it could have two or three sides that are all equal length. The third one down says equilateral, all sides of equal length. So an equilateral triangle means that it's going to look the same on, no matter what side you flip it, it's going to look the same. Mine isn't exactly equal, but you guys get the picture. The next property says regular, all sides of equal length and all angles of equal measure. So something that is regular. In this example, they've given a hexagon where all of the sides are of an equal length and all angles are of an equal measurement. Another example of something that is regular would be a square, because all sides are the same length and all angles are equal. They are all right angles. When we are using math pictures, if you draw a line in between the sides, that represents that this side is equal to this side is equal to this side is equal to this side. If I were to draw a rectangle where I do not have all equal sides, in order to show the sides that are equal, I might do one line here and here representing that those are equal sides, and two lines here and here representing that those two are equal. So a little bit of math fun facts for you. Irregular means at least one side and one interior angle are not equal in measure to the other sides and angles. So again, they've given you, actually I think they've given you the example of a septagon. 1, 2, 3, 4, 5, 6. Nope, it's still a hexagon, but all of a sudden it has this pointy Pinocchio-like nose on it. Right, at least one pair. A right shape has at least one pair of perpendicular sides. Perpendicular means that the lines intersect, forming right angles. So these would be perpendicular lines. And in this example, they have a shape that has two perpendicular lines. So if we were to extend this one and this one, and this one, they all cross. And they show you that your opposing angles are right angles. So if you have a little box that's drawn in the corner like this, that means that your angles are right angles. And then the last one says parallel sides. So parallel lines are two lines that will never meet. So if, that's horrible. That's a little bit better. If we were to continue these lines on forever and ever and ever and ever and ever in both directions, they would never cross. So depending on the angle of your lines, you might have some that look like they're parallel, but if they're even ever so slightly off, at a certain point they will meet. But if you have parallel lines, they will never meet in time or space. Okay, underneath it says think. Can a polygon be categorized in more than one way? So let's look at some of the examples that they've given. A regular shape, all sides of equal length and all angles of equal measure. Are there shapes that can be regular as well as one of the other categories? Why don't you take a look at your table and see if you could see which category, what other category might fit with the term regular. If you said an equilateral triangle, you would be correct, because if all of my sides are the same on my equilateral triangle, I'm going to draw my lines that represent that all sides are the same. I also need to have all of my angles be the same so that they will all add up. So an equilateral triangle would be an example of a regular shape, meaning that polygons can share more than one attribute or property. Okay, so it says think about how a quadrilateral is defined. It is a polygon with 4 sides. So any shape with 4 sides can be both called a polygon and a quadrilateral. So remember, polygon can be any shape as long as it meets those 2 requirements of no curved lines and no open areas, no closed, all closed sides. So any shape with 4 sides can be both a polygon and a quadrilateral. But if the quadrilateral has 2 pairs of parallel sides, then it can also be called a parallelogram. So a parallelogram is just one type of, that's not very good, anyway. A parallelogram is just one type of polygon. Under that definition, we call it a quadrilateral because it has 4 sides. And under that category, we call it a parallelogram because it has 2 pairs, now it does, of parallel lines that will never meet in time or space. So under one heading, you can have different subheadings that get more and more specific to the attributes of certain shapes. Every parallelogram is a quadrilateral because every parallelogram has 4 sides, but not all quadrilaterals are parallelograms because not all quadrilaterals have 2 pairs of parallel sides. You may have heard people say a square is a rectangle, but a rectangle is not a square. The reason for that is because the rules that dictate a rectangle, that you need at least 2 sides of equal length. You need at least 2 sides of equal length. So this side and this side and this side and this side. And you need 4 right angles. Those rules would still apply to a square. My goodness. See what happens with the last lesson? I just fall apart. Where's the tissues? Okay, so a square would also meet that category. This side and this side are equal. It just so happens that this side and this side are also equal, and you have 4 right angles. So a square could be categorized as a rectangle. A rectangle, however, could not be categorized as a square because a square is more specific. All sides have to be equal in a square. So that's just kind of to demonstrate again that you can have shapes that fall under different categories, and some of them get more and more specific with the properties as you get farther down in the name chain. So on the next page, we're going to be talking about, it says, think, how can you show the relationship among polygrams with a diagram? A Venn diagram is a useful tool for organizing categories of polygons that share properties. So you guys have seen Venn diagrams that look like this. So you have one category over here, another category over here, and then attributes that they share in the middle. Beneath, you see that they have a very different shaped Venn diagram that of triangles. So they have, so it's all, the whole square represents triangles, but then they have overlapping ovals and circles and things like this. That show you that there are some triangles that fall within the same category or share certain properties, but they're all still considered triangles. Underneath it says, notice the right category partly overlaps the isosceles category. This means a right triangle may also have all the properties of an isosceles triangle. Also notice that the right category does not overlap the obtuse category. That means a right triangle can neither have the properties of, can never have all the properties of an obtuse triangle. The equilateral category is nested completely inside the isosceles category. This shows that equilateral triangles are a subcategory of isosceles triangles. So all equilateral triangles share all the properties of an isosceles triangle. So we talked about that before. An isosceles triangle, remember, has at least two sides that are the same length. An equilateral triangle has all three sides that are the same length. So therefore, an equilateral triangle meets all of the properties of an isosceles triangle. But again, an isosceles triangle wouldn't necessarily be an equilateral triangle because it may or may not have a third side that, that is the same as the other two. Okay. Question 1 says, what does it mean that the Venn diagram shows obtuse partially overlapping isosceles? So remember again that when they overlap, they share some of the same properties. So that means that obtuse and isosceles triangles can share properties because they're partly overlapping. Okay. On the next page, it says, number 2 says the Venn diagram shows categories of quadrilaterals with different properties. Write the name of each category that fits the description. So A, it has 4 sides. That means that it's a quadrilateral. Any shape that has 4 sides, we call it a quadrilateral. That is the biggest circle because it's incorporating all of the other aspects. Within that, it says at least one pair of parallel sides. So any quadrilateral that has at least one pair of parallel sides would be considered a trapezoid. Inside that circle, you have one that says 2 pairs of parallel sides, which we would call a parallelogram. And then within the 2 sets of parallel sides, there are 2 overlapping circles. One that says 4 sides of equal length. That could be a rhombus. And 4 right angles would be a rectangle. And one that combines both 4 sides of equal length and 4 right angles in the middle section there would be squares. So I'm going to show you, I'm going to give you a sneak peek at the teacher's edition here. So outside is quadrilaterals. Within that, trapezoids having at least one pair of parallel lines. Within that are parallelograms that have 2 pairs of parallel lines. Within that category, there's one side that says that it has 4 right angles. That would be rectangles. The other side says it has 4 equal sides. That would be rhombuses. And the one that share the name of what shares both of those properties would be a square. So you are probably thinking to yourself, who cares? Because why are we going to classify shapes this way anyway? Well, 5th grade standard says that y'all got to know this. So that's why we're doing this. But it's also kind of cool because you can see that shapes can be really specific, like squares, or they can be really general, like quadrilaterals. And so this is just a visual way of representing that. May not be your cup of tea, but too bad. Okay, number 3 says use the Venn diagram to fill in the table below. So I'm going to go ahead and skip through this because I want to make sure that we have time to get into the real part of this lesson. This is just kind of giving us an overview. So I'm going to skip on over to page 311. Yep. And number 4 says, is every property of parallelograms also a property of all rectangles? So remember with our chart, we have parallelograms, and then within that, we have rhombuses, rectangles, and squares in the middle. So I've just kind of taken that subset. This would be parallelograms, rhombuses, rectangles, and squares in the middle. So because rectangles are within parallelograms, yes, all rectangles share all the same attributes as parallelograms because they're totally within the same circle. Now, if rectangles only partially overlapped with parallelograms, they might share some of the same attributes, but because rectangles is embedded within parallelograms, yes, they share all of the same attributes. The second part of that says, is every property of rectangle also a property of a parallelogram? No, because it does not go the opposite way. So remember how we talked about how a rectangle could be considered a square, but a square could not be considered a rectangle? A rectangle is a type of parallelogram, but a parallelogram wouldn't necessarily just be a rectangle. So every property of rectangles also a property of parallelograms? No, because parallelograms can look like this, and one of the properties of rectangles is that it needs to have four, oh my good gracious, 4 right angles. Okay. The third part of question 4 says, explain what the Venn diagram shows about the relationship between rectangles and parallelograms. Basically, it's saying that all rectangles are parallelograms, but only some parallelograms are rectangles. So all rectangles are parallelograms. They all meet the same categories, but not all parallelograms are rectangles. Okay. We're going to go ahead and skip to the middle half of that page that says try it another way. So you can also show this as a flow chart. A flow chart is just supposed to direct. We've done flow charts before with fossil fuels, you may remember. So you have one thing that leads to another thing that leads to another thing. So flow charts can be a way also of visually organizing your information to show what things are alike. So this one shows a flow chart of quadrilaterals. So all quadrilaterals lead to trapezoids. All trapezoids lead to parallelograms. Parallelograms can then verge off and be either rectangles or rhombuses, and then rectangles and rhombuses meet once again in squares. So once again, quadrilaterals to trapezoids, trapezoids to parallelograms, parallelograms to rhombuses and rectangles, and rhombuses and rectangles meeting back again with the attributes of squares. Okay, again, so 7 says, in every rectangle, the 2 diagonals have the same length. So in a rectangle, if you can draw a rectangle. In a rectangle, if you were to take one corner and pair it with the other corner, and do that with both sides, this line and this line would have the same length, always. So it says, therefore, in every parallelogram, the 2 diagonals must have the same length. So is this true or false? Let's go ahead and try it with a picture. Here's an example of a parallelogram. I'm going to draw one line here and one line here. Do my lines look like they're the same length? No, they're not. So that would be false. You can have, and again, remember that's because parallelograms, all rectangles share the same attributes as parallelograms, but not all parallelograms share the same attributes as rectangles. So something that applies to rectangles wouldn't necessarily apply to all parallelograms. Okay, question 8 says every rhombus has at least 2 lines of symmetry. Lines of symmetry mean if you cut it in half, it looks exactly the same on one side as the other. So okay, so a rhombus kind of looks like this. And what they're saying is your lines of symmetry would be like these imaginary lines that cut your shape in half. And if I cut my shape in half this way, it would look the same on the top as on the bottom. Now I'm going to go ahead and flip it and do the same thing. Cut it in half this way. This is now my new line of symmetry, and it also looks the same top and bottom. So with a rhombus, you can flip it either way, cut it in half, and it will look the same on both sides. For it says, therefore, every square has at least 2 lines of symmetry. So remember, squares are within the subcategory. They share attributes of rhombuses and rectangles. So let's think about a square. If I cut my square in half this way, it looks the same on both sides. If I cut it in half this way, it looks the same on both sides. So therefore it would be, because it shares the same attributes as rhombuses, yes, you would have 2 lines of symmetry in a square, just as you would with a rhombus. Okay. I'm going to pause for a second just because I feel like this may be confusing to some of you, because some of you may have, I think geometry often gets short shrifted in math, because oftentimes in the progression it's kind of left until the spring, and as you guys may have experienced in past years, things get pretty rushed in the spring. There's testing, and so you may not have encountered some of this information before. So I'm throwing out words like rhombus and parallelogram and trapezoid, and you may have to kind of dig back to using those pattern blocks. You may have learned about those way long ago, the names of those shapes, and you may never have discussed the properties. So this may be new information. Please be kind to yourself. It's okay if you don't fully understand this. This is new material. What I would encourage you to do, work through the problems in the book as best you can. Meet me at the Google Hangouts if you have questions. And be patient with yourself. Rewatch the video, pause it, come back to it, do what you need to do. But this is new information. So a lot of it may be confusing, and I'm going to do my best to try to explain the parts that may not have been explained before. But just be patient with yourself. If you don't get it, it doesn't mean anything about your math abilities. It just means that this hasn't been explained to you before. So I'm going to do the best that I can to try and fill in those gaps. But if you're like, meet me at the Google Hangouts, work through the problems in your book, rewatch this video, and hopefully we'll get it. Okay? Okay, so now we're going to turn back to the previous lesson, which starts on page 302. So now you're going to turn back in your books to page 302. And now we're going to be talking about ordering shapes in a hierarchy. So a hierarchy would be like if you have Lord Peach at the top of everything, then he oversees everything else. So then he would have his minions, Orange and Pineapple, who would be next in line. They would be the, kind of like the supporting, the dukes and the earls and things like that that would be under the king or the lord. And then from there, you might have all these additional players as well, like tomatoes and grapes and raspberries and blueberries and things like that that would also fall in categories down here. So, so a hierarchy is just another way, if you think about a flow chart and you turn it on its head, then it becomes a hierarchy. Okay, so on 302 it says, read the problem below, then explore different ways to classify figures in a hierarchy. Classify the following triangles from the most general to the most specific scalene triangle. So again, remember, we're talking about attributes. They go from general to more specific the more specific ones don't share other attributes with the more general ones. So you have a scalene triangle, isosceles triangle, and equilateral triangle. Use a tree diagram to classify them as types of triangles. So the first example says model it. You can understand the problem by listing the properties of the triangles in a table before arranging them in a tree diagram. So isosceles has 2 or 3 sides of equal length. Scalene has no sides of equal length, and equilateral has 3 sides of equal length. So then you can think of your hierarchy. We're going to start with our general category of triangle, and then we're going to think, I know that isosceles triangles with 2 or 3 sides of equal length share some attributes with an equilateral triangle, which is just 3 sides of equal length. A scalene triangle has no sides of equal length, so it doesn't share anything in relation to the other two. So I'm then going to draw 2 branches off of my tree, and I'm going to go to the next more. So triangle is general. We're going to start getting more specific and saying that scalene with no equal sides has its own category, and isosceles on the other side has 2 or maybe 3 sides of equal length. From there, we have one more type of triangle, the equilateral triangle, which would fall under that category of isosceles. I'm not even going to try to do that upside down. So general triangles, we break it into 2 different components, those that have no equal sides and those that have 2 or 3 equal sides. And from there we get even more specific, saying just has 3 equal sides. Okay. On the next page, on 303, it says, why is triangles in the top row of the tree diagram? Because we're going from general to specific. Triangles would be the most general category, or category or label that we would give it. So that's why triangles is the top category. It is the most general. Number 3, write scalene and isosceles in the second row of the tree diagram at the right. Why are those categories separate? Because they don't share any attributes. A scalene triangle has 0 sides that are equal. An isosceles triangle has 2 or 3 sides that are equal. So those don't share any of the same attributes. We can't link them together. Therefore, they're going to be 2 totally separate categories. Number 4, write equilateral beneath isosceles. Why can all equilateral triangles be classified as isosceles triangles? Because isosceles triangles can have 2 or 3 sides that are equal. Equilateral triangles have 3 sides that are equal. So they would fall under the category of isosceles triangles because they could meet the same definition. Number 5 says, how can you use a tree diagram to order figures? So starting with the most general to getting more and more specific with each subcategory. Okay, number 6 says, try it. It says, complete the Venn diagram below to show the hierarchy of isosceles, scalene, and equilateral triangles. So you have, I believe, something that looks like this. So your whole topic is triangles. You have 2 separate topics, one that has another topic embedded within it. So if we look back to your tree diagram, we'll see that we're talking in our most general space about all triangles. And then in our 2 subcategories, we have isosceles triangles. and we have scalene triangles. Those are separate because remember they don't share any attributes. And then embedded in isosceles, we have equilateral triangles. I can't fit it in there. That's embedded in there. So same principle, just a different way of displaying that information. Okay. I messed up. We started in the middle of the lesson. So, sorry guys, scoot on back to page 300. And it says, in this lesson you will classify polygons based on their properties. Take a look at this problem. So it says, arrange the polygons below so that a polygon can also be called the name of the polygon before it. Order them from left to right. So you have 3 examples of quadrilaterals. You have a rectangle, and we can tell that it's a rectangle because if we count the squares, we have 4 squares going across and 2 squares going up and down. We have a parallelogram, and we have a square, and we can tell that it's a square because it has 3 squares going across and up on all sides. So we have something that looks like this. So it's saying arrange the polygons below so that a polygon can also be called by the name of the polygon before it. So if we were to rearrange these, remember we're going from general to more specific. So remember we would have parallelograms first. So if I were to redraw my picture, I would have parallelogram first, followed by rectangle, because all rectangles would meet the requirements for being parallelograms, but not parallelograms meeting the requirement for rectangles. Then I would have my square, because squares meet the properties of a rectangle, but rectangles do not meet the properties of a square. Yeah, so because we kind of went out of order, I'm just gonna, I think from dealing with the triangles that you guys probably understand this, these problems are working the same way. They're just working with 4-sided shapes instead of 3-sided shapes. So I'm going to go ahead and what I would recommend is working through those problems on your own for added clarity. But if you are like, nope, I totally got this hierarchy thing, you can just go ahead and jump onto the practice pages. Practice pages are going to be a little bit more extensive because we've covered 2 lessons. I'm going to say that 323 and 324, that's 1 double-sided page, is required. 325 and 326 would be optional but recommended. And then 331 and 332 would be required. And 333 and 334 would be optional but recommended. Lastly, because this is your last lesson, this also means that you guys are at the end of a unit. So I would also recommend, but not require, taking a look at the performance task and trying to work through it. The reason I am not requiring it is because I know that some people may not have the same incentive since it's not going to be graded. And I know that they are very time intensive and brain intensive. And so I know that that may be more effort than you guys are willing to put in without a teacher there holding you accountable. So I get that. Why I would recommend it would be because the whole reason that we've been doing the performance tasks is because that is a format that you are going to continue to see throughout your schooling experience. So the more practice you get at organizing your information and your thoughts, the more practice you get at producing in your work a logical flow of first, next, then last, the more that is going to help you throughout your math career. And it also just helps with solidifying the information that you've learned. It also just helps clarify. So there's a lot of good that can happen from that. But again, I totally understand if that's not really something that you want to do on a beautiful spring day when you're at home and you could be jumping on your trampoline instead. So I get that, but there is value if you feel like tackling the performance task. That would be awesome. If you do decide to do it, send me a picture, and I will happily send you something in the mail in return. Okay, with that, you guys made it. You guys are amazing. You've worked really hard this whole year on this math. You should be so proud of yourselves. We have about a month and a couple of weeks left in this school year. And I know that you guys as fifth graders are probably looking at that like, first of all, like it's a big bummer because it's kind of an anticlimactic way of marking your succession from grade school to middle school. I'm hopeful that we can have some ceremonies to celebrate all of the hard work that you guys have done at the end of the school year. We're going to stay tuned for that. In the meantime, this is your last math lesson. So once you guys are done, you can do what you like with your books. I really hope that you guys take, as you do whatever you do with your books, I hope that you take a little bit of time to really pat yourselves on the back and sit and soak in the accomplishment of having completed every single math lesson in that book. That's huge, and you guys have worked so hard and so diligently, and I'm so proud of you, and you guys should be so proud of yourselves. So this will be your last math lesson that's posted. You guys are still more than welcome to come and join in Google Hangouts, but you're off the hook for the math lessons from here on out. So keep up with your iReady online. That's really important because that's going to help us as we transition back to what regular schooling is going to look like. It's going to help you continue to build on and boost the skills that you guys have learned throughout the year. Yeah, enjoy that little bit of freedom of having that pressure taken off. Go and do something to celebrate. Do some art. Eat a yummy treat. Do something that feels festive because you guys made it. Hooray! And like I said, if you do decide to do the performance task, please send me a picture, and I will happily send you a little something in the mail in return. Okay, love to you all. Hang in there, and I'll see you around. Okay, bye.